Dude, this week is kind of epic, okay? First off, my Discord server got partnered with Discord, okay? So that's kind of crazy. We've like been revamping the whole thing. We've added we've made the channels a lot nicer. We've like added a bunch more roles. We're gonna be running events now too. So if you guys like math, you guys like science, you guys like any of that stuff, please join the Discord. There are a bunch of cool people there. You guys can talk about whatever the heck you want. And you can participate in our events, okay? I might even be participating in them too, so you guys can fight me 1v1. Let's do it. But yeah, join the Discord. It's very fun. It's partnered now. It's very official. We even got banners and stuff. Also this weekend, I don't know whether this video will come out after or before I do this, but we're going to be releasing a subreddit, so you guys can post all the very STEM related memes you guys love to post in like my Discord. You guys can put it there, and we might have some brain dead Reddit reviews at some point, who knows. And lastly, if this video is coming out on Sunday, you guys will know that I will be streaming at 4 to 6 that day, okay? And you guys can ask me whatever the heck you guys want. But literally on Thursday, I started accidentally streaming. I just wanted to see how like the streaming thing works, and I accidentally started going live, and a bunch of you guys jumped on and asked me questions. I'm sorry I ignored you guys, but like, I couldn't even talk to this camera. I was just testing it out. So yeah, look forward to that too. But this video is not just to plug very random stuff that's going on, although I hope you guys take advantage of it. I hope it's helpful for you guys. Please let me know in the comments if it is helpful. But other than that, let's get into the video, okay? I still haven't done silver because I've been so busy I haven't had time to actually make a full silver video, so let's get into it. Hello everybody, I'm Karara, and today we are going to be doing the US 2020, wait what, no, USACO 2021 US Open, that's how you say it, silver contest, okay? Let's get into it. Maze Tac-Toe. Dang, that sounds scary. Bessie the cow enjoys solving mazes, okay? She also enjoys playing tic-tac-toe, seems legit. And Farmer John has found a new way for her to play both games at the same time, bruh. Okay, so instead of placing X and O's in a 3x3 grid, they play with M's and O's, okay? And during one turn, they can either place an M or an O or on any empty grid square. So, okay, I see. And the winner is the first person to spell moo, horizontally, vertically, or diagonally backward is fine. And let's see. It is possible to, yeah, okay, so you might not win. And that, okay. So, basically, Bessie has to go through a square maze of n by n cells, okay? Some cells, including border cells. Okay, bro, why is it so long? God dang it. And, so she can move in any 4 directions, north, south, east, or west. Some cells contain a piece of paper. Okay, so this is what's telling her what move to do in the tic-tac-toe. And then, once she steps on a cell, she must make the corresponding move while she moves, unless it's already occupied, in which case she ignores it. Okay. She has no opponent, but basically she wants to eventually get to move, okay? And she stops immediately upon winning, finds the distinct ways of winning. Okay. Huh, that was a mouthful, holy moly. Okay, so you have 3 end characters, so this is like, this whole thing is one cell, and then this represents a move, and then this is like an empty cell, and she starts over here. Okay. So essentially, if we want to get a move, we could like go up here, down here, and that. No, you need M33. Okay, so you could do like, I mean, yeah, you go like here, get the M. That works. Okay. Oh, but there's 8. Okay, so there's a lot of different options. I mean, I guess like you could see like if you take these two and this one, if that's what you want to make your winning line, right? Then you know you have to get through this one, right? So the only one where it's like 1 1 2 2 3 3 is like it has to also have 032, which is this. Okay. Yeah, you can see all of them have the 032. And then you could like take any subset of the remaining ones, right? Oh, but you can't win before. So, Well, actually no, but she could always go here, take whatever she wants, and then go back here, and then take whatever she wants, and then go here. Okay, you know, let us put it in Photoshop. This is kind of nasty seeming. Like, even if I get the solution, I feel like the implementation is going to be disgusting. Holy moly. Bruh. Okay, let's just try to figure out something nice, though, if there's a easy way to do it. So, we could basically draw it like this, right? Let's just say we got like this, like that. And then we could say we got like a thing there, okay. Then we got like, and you got an X there, you got your Bessie over here, you got something there, you got something there, and you got something there, and you got something there, got something there, there, and there. Okay. So basically the idea is we want to like figure out a dependency on the moves, right? Like basically like if you want to get to this move, you have to go through this move, right? If you want to get to this move, you have to go through this guy. And if you want to go to this guy, you probably have to go through this guy, which means that you also have to go through this guy, right? So essentially we could like have transitive property, right? Like eventually it has to go back to Bessie. So that is relevant. So let's just say we like found this tree, right? We have like we have Bessie could either go to any of like some basic ones, right? She could go to 011 directly, she could go to 022 directly, and she could go to 032 directly, right? Then from 022, she could go to M13 or M22, right? Then from 032, she could go to M31 or M33, and then from M33, she could go to 031 and M11. Okay, so this is like the only order you could do it in. And once we have that, how could we actually get the tic-tac-toe nonsense? That is the question. Bruh. I don't know. This is kind of nasty though, right? So, obviously, like, okay, so first you had to figure out ways of winning. And, like, a 3x3 board is, like, really tiny. You could just go through all possibilities and see if they win or not. So, So, is it better? Okay, well, let's see. How long would it take to traverse all of these? Well, okay, the problem is that you basically had to choose like some height on each of these branches, right? Like you could either take like you could take this one, you could take this one, you could take this one, take this one. Well, let's see. Yeah, going through all possibilities would be a bit excessive, right? N is 25, so you can't really. Well, 25 is tiny, so you could. I think you could. No, but 25 times 25 is kind of nasty, right? Yeah, you can't do like you can't like do exponential in n squared. That's not gonna work. Okay, so I guess we could just go through like each branch, right? So this branch could generate 011, that's the only option. This branch you could generate like 022, 022 M13 or 022 M22, right? Then this one can generate 032 M or the 032, 032 M31, 032 M33, and then like just adding on those. And essentially you want to put these together so that like you get a winning thing. Well, okay, so basically these are in a group by themselves like that. And you basically want to add like one from each group maximum and try to get a winning thing. Okay, so basically like, it's basically like, so the sum of these could be maximum like 625 different like moves, right? So there's 625 of these guys, and we could, if we split it up, then that might be too big, right? Because you could have like groups of 2, and a lot of the groups of 2, and that would be bad. So what could we do? Why don't we like took the board first? Like let's just say we have like M-O-O-O, and then we figured out if it was possible, right? So essentially we could see how do we get this one, right? We could either like obviously 0 and 1, we could take this, right? Then let's say we wanted 022, we could either take this one, or this one, right? Let's say we took this one, then it would be, well then this one would not work, right? Because then like you would get an extra and that's not good. But then this one is fine, right? So we could take this one and this one. Yeah, we could just like go through it greedily, right? Like we could just go through each one. Does it fully go in here? Like, and then if it does fully go in here, then we take it, right? Luckily you can't do it greedily, right? Because you don't want to win before you get to the other one, Wait, yeah, because order matters, right? Like if you don't want to win too fast, then you got to do it in a certain order. That's annoying. Do we have to like list out every single possible board that you can make even? Or let's see. I mean, you could fix this one and then go through all of the other ones, but that'll take way too long, I'm pretty sure. So, well, okay. I don't really know what to do because, okay, so we for sure start with this tree, right? So we have BBB, we have 032. Okay. So essentially the idea is we want to get all possible boards Bessie can find and then check if each of those work, right? That's probably going to be the best way to do it because checking how it works is pretty easy, right? So, how should we do this? So the problem is if you like go through all possibilities, right, that would be like way too long because you gotta go like here, you could go backwards and all that stuff, so that's nasty. But we know that each of these edges consists of going from something that like has an O32 to something that has like an M31 now, right? And essentially like if we keep track of possible boards, right, then there could only be like 3 to the 9 possible boards, right? So we're only checking 3 to the 9 possible things, so it shouldn't be too bad if we just DFS. Okay, why don't we just implement that? So we can find this thing, and then we should be good. Okay, so basically the idea is, what we're going to do is we're going to generate that tree, right? And once we have the tree, we're going to generate all possible boards you can make from that tree, right? We're going to like start with a blank board, right? And then we're going to go like to the first one on the tree, which is BBB. And then we're just going to like go through all of them, right? We could either go to 011, then we would just put an O there, right? And then from 011, we could either go anywhere back on the tree, like whatever, right? We could do all that stuff. Or we could go down the tree, right? And then we could update them with new moves. And we'll just keep track of like our current board and the like current place we're at, right? So at this place we could be at a bunch of different boards, and then from each of these boards you could make a new like board by going on any of these edges. And we'll just implement a very fat BFF. Okay, let's do it. Okay, so we got using namespace, we got our int n, okay, we got our grid. So how do we store things easily? Why don't we have like a pair of, I don't know, let's type as parent int. And we can basically store the type of thing, like if it is a wall, we'll like put 0, if it's a normal thing, we'll put 1, and if it's a move, then we also want to store like what the move actually says. So pair of int, and then like the move, what the move says, it could be 1, 1, 2, 2, etc. So we'll say parent int, okay. What do we call R? How about that? Okay, so let's read everything in. And then we'll say R of, well, okay, this has to be less than like 3 times then, because we had to like see in everything. And then this should be j plus equals 3. And we got to do string s, and then like cns, okay. Or actually we should just do this, and then we could fiddle around with it later, okay. And then essentially we got our rij, we could probably do a switch, right? Yeah, okay, so we will do switch on the first element, which is going to be s 3 times j, right? And essentially the first case is if it is equal to a star, so that, or no, hash, okay. Then we say, let us write a comment over here so we don't confuse ourselves, hold up. So we'll say 0 is a wall, 1 is a nothing, 2 is a Bessie, 3 is a O, and 4 is a M, okay. So in this case we basically say Rij is equal to 1, comma, let's see, what are we going to do? We can say, yeah, 0, comma 0, it doesn't really matter. And then we just do it for the rest of the cases. And this should be 50 by 50. Okay. Whoops, this should be a 0. O is going to be 3, and then S 3 times J plus 1 minus 0, and same for the next one. And then we copy paste this for the M, and we should be good. Epic. Okay, so we read everything in. Now we just got to do fun stuff. Oops, I have too many. Okay. So now the idea is we basically want to like BFS from here, right? Or do we want DFS or BFS? Well, how do we do this quickly? Well, okay, so the first step we could do is we could like generate an adjacency list, right? Like we could generate that tree, so why don't we do that? And basically the way we're going to do that is we're just going to have like, do like BFS from here, get all the things you can reach from there, do BFS from here, find all you can reach from there, and so on and so forth. So, we got to keep track of our starting points. Vector, I don't know, what should we do? PII starting points. And then every time we get a Bessie, that should be our starting point, right? So we would do, well, we should give each one a number, right? Because that would make things a lot easier for us. I mean, we could just store it based on like a position. So we could just do our adjacency list is like, pair. We'll do, yeah, we want to do a map of a PII to a vector of PIIs. Okay. And this is how we're going to store our graphs. Okay. So every time we want to BFS from B, we want to BFS from all the moves as well. So we'll do starting point dot pushback I comma j. Epic. Okay. Now we gotta run BFS from all of them. Fun. Right. Okay. So when we do BFS, we always have our adjacency thing: 0 1 1 0 0 negative 1 and negative 1 0. And we'll go for PIIP in our, let's see, for in our starting points. Then we basically want to BFS from there, so we need a visited array. And at the beginning we gotta reset it every time. For int I equals 0, I less than n, I plus plus. For int j equals 0, j less than n, j plus plus. And we will say visited ij is equal to false. Nice. And now what do we gotta do? What do we gotta do? That is the question. Then we gotta do visited of our p dot first, p dot second is equal to true. Then we gotta do q dot push p dot first, or just p. Okay. Should be, that's right. Okay. Oh, I called it q. It should just be q. Q is a lot easier to type. Alright, nice. Then while the q is not empty, we will go through all of its adjacent dudes for int I equals for int, or no, pair I dir in adj. Then we're basically gonna say next int next m is equal to p, or wait, we need to get our current pair before we actually move from it. Okay, PII's car is equal to q dot front, and then q.pop. Next m is equal to car.first plus dir.first. Oh my god, why is this such a fat impl? Holy moly. Next n is equal to car.first, or second, plus dir.second. And now we gotta check if we can actually move to the next m or next n, and then we should be good. So, if not visited, next m, next n, and next, or like r, next m, next n, dot first is not equal to 0. Well, it should be equal to 1. The only thing we care about really is equal to 1. Then we basically do q dot push next m, next n. If the r, next m, next n dot first is not, like, if it's either an o or a, if it's either an o or an m, then we are good. So if it is greater than 2, then we don't want to actually push it because we don't actually want to continue. Well, first we gotta set this to visited, but we want to add it to the adjacency list of our current guy. So we do graph of our starting point, which is p dot pushback next m, next n. Okay, nice. Well, okay, we don't want to push it back twice, so we should probably use visited. If not visited, okay, and then put this inside. If that, then we do that. Otherwise, we will do this. Alright, very epic. So, now, okay, I did not set it to anything, is equal to true. So, the next strategy we gotta do. Okay, so I think this should, like, give us all the adjacency stuff. Yeah, that should be fine. And then, once we have the adjacency stuff, now we could actually do the fun, go through all the possibilities. So, the way we are gonna represent a grid is using a number, right? Like an int, right? So, each of the 9 spots could be 0, 1, or 2. We'll say 1 is a O, 2 is an M. So essentially, there are 3 to the 9 possibilities, in which case, that basically means that we could represent it with a base 3 number from 0 to 3 to the 9, or like 1 less than 3 to the 9. So when you have nothing on your grid, it'll start at 0, right? So we'll make our new q, right? We'll just do q.push 0, and we'll make a visit array. So bool boards, visited board, vboards, and then that'll have to go to 3 to the 9. What is 3 to the 9? What the heck? 3 to the 9. 1963. Wait, that's not what it said. 1963, what's that do? 20,000. Vboards 0 is equal to true. Well, actually, okay, we kind of care about what location you're at currently, right? So essentially, we need to make our queue a little bit more complicated. We'll need a new queue then. B. We'll just call it B because it's like boards, and it should have a pair of the actual. It should have a pair of the grid, tic-tac-toe grid, and the current location. So like that. Q.push 0, comma, the actual B location. So we need to figure out the B location. So we'll have a parent I, Bessie, and Bessie will equal the location here. So while not B.empty, so essentially we look at the possible moves you can make from going to Bessie, right? So you look through its adjacency things, then you make the move corresponding to it, right? So essentially making a move literally just means you add to it, right? You just add like plus I don't know. Yeah, you just do like plus the value of the move, right? Like 0, 1, 1. That's like index 0 in the tic-tac-toe grid, and the O contributes 1, so you do 1 times 3 to the 0 is equal to 1. So that's how we do it. So we will do PII or pair int PII car is equal to b.front and then b.pop. And essentially, we should probably like if visited vboards. Well, actually, this might be a little bit complicated, right? Because we could visit any board and like location pair. That matters. Okay. Wait, could we visit any board location pair? That would be like 20,000, 3 to the 9 times 625 over 10 to the 9, I guess. 10 to the 8. Okay, so it seems small enough. So we will make it actually vboards. We'll make it a map of a parent int to a pair of pair int or a pair of int comma pi. Holy, this is so confusing. Bool. Okay. So we said vboards 0 comma Bessie is true. If vboards like B or car, then we want to just continue. Otherwise, we want to make all the possible moves, right? So we just go for like what's in our graph? It is a bunch of pairs. So for PIIP in graph of car dot second. So essentially these guys should all be moved, right? So essentially we take the move from that location and we apply it to the board. So we essentially get move or int move is equal to, or okay, so we'll say like move or pair of int comma pii move is equal to r p dot first p dot second. So that's just like recovering it from the grid, okay? And then we'll say move to like a number, move to int. So the way we do that is we take the first element of the move, right? And we know that O is 1, but it's originally a 3, so we gotta subtract 2. Move dot first minus 2. And then we multiply it by its location, right? So the first row is 0, 1, 2. Second row is 3, 4, 5. Third row is 6, 7, 8, right? So we could do 3 times move dot second dot first plus move dot second dot second. And this is actually one index, so we gotta subtract 4. Okay. So once we have that, we can basically say our new board is adding to our old board. So our new board is like car dot first plus that. And essentially, we don't even have to think that much, right? We just say visited. Okay, so int new board is equal to car dot first plus move to int. Oh, we also had to check that the current what? The current board doesn't already have something there. If it already has something there, then we don't actually change it. So how do we do that? We would have to check. Okay, so we could check in graph or in grid. So bool in grid, we'll take in the grid and we'll take in the move. And the way you check if it's in the grid is you basically divide out the move and then see what's left. So while move is greater than 3, then essentially we just do grid over equals 3, move over equals 3. And we basically just say return grid mod 3 is greater than 0. Okay. Because basically like this will make it so that like the move is just like one base 3 digit, right? So essentially you want to find that digit in the grid and see if there's already a digit there. So if there's a digit there, then we don't actually change anything, but if there isn't, then we do. So int new board equals car dot first if not in grid our new board comma the move we want to make, then we do new board plus equals move to int. And if our new thing, if not vboards like new board comma p, then we will put it in our queue, b dot push new board comma p. Okay, and we will mark it as visited. Epic. Okay, so now at the very end, we basically just go through all the possible boards and see how many are visited, and we should be good. Oh, and we also have to check if they're winning. we gotta make sure that it's actually winning. So we will make a check winning function. Or actually, why don't we just like print out all the possible boards we can make? So I'll make a quick function to print out display grid. So void display grid int grid. So the first digit is like in the first spot, the second digit is in the second spot, and so on. So we could basically say for int I equals 0, I less than 3, I plus plus. For int j equals 0, j less than 3, j plus plus. And essentially we could do cout grid mod 3, or actually wait, we should probably do, well, I think this is fine. And then we do grid over equals 3, and at the end of each line we do cout end up. So for int I equals 0, I is less than, okay, powers of 3 are pretty important, so I am going to make a power function myself, so we know how to deal with doubles. So int power, this is just clear exponentiation. You guys, like, I mean, recursive exponentiation, it shouldn't be too complicated. So int a, comma int b, and essentially all you gotta do is, if it's even, if b mod 2 equals 0, then we could just square the result of dividing this by 2, in which case we do int ret, or we could use int ret either way. Int ret is equal to pow a comma b over 2, and then over here we return ret times ret. Otherwise you return ret times b a. Okay, and if b equals 0, then we return 1. So less than pow 3 comma 9, right? And then I plus plus if okay. So I guess we should probably do a vboards like overall. So bool v good boards g boards is equal to, or like, and then this is like 20,000. And if we ever get to one of these, we'll just say gboards 0 equals true, and over here gboards new board is equal to true. If gboards I, then we just display grid I, and we will do cout endo. Okay, let us test this out and see if we get the right stuff. Okay, so we're not getting the right stuff. Hold up. Okay, so that is for sure working, but then this is not. So if vboards car, then continue. Oh, we never push? Oh, we do push. Wait, what? Okay, let us cout p dot first, p dot second, and no. Okay. Oh, what? Okay, is our graph is not working? Let's see. For int I equals 0, I is less than starting points, I guess. I is less than starting points dot size. Or no, we can just do for pii and starting points. And then we'll go for int I equals 0, I is less than graph. Or no, we can just do for int I in no, for pii in graph I. Okay, or p. And we just do cout I dot first, I dot second, and then we do cout. Okay, so our first guy, which is this guy over here, is adjacent to only one other guy. Hold up. 2, 3. Okay, maybe we should do greater than or equal to. I mean, even then, oh, I guess that is right. Okay, so 2, 3, 4, 1. Okay, that's right. Seems legit. Very legit stuff. Okay, and then we'll take out this. Oh, let's see. 3, 4, 2, 3. 3, 4, 2, 3. So yeah, this guy, yeah, okay, that is right. And then 3, 4, 1. Yeah, okay, that's this guy. And all these guys. Okay. Over here, we'll cout car. 0, 4, 1. No, okay, so 0, 4, 1. Okay, that's right. Then it doesn't. Okay, vboards. Oh, okay, we just don't need this. Okay. That should be fine. Vboards, new board, p. Okay. None of you went past the, or did they? They went past 3 to the 9, so there's the problem there. 19683, so I don't know how it got past 3 to the 9. What the heck? Okay, so it has to be not in the grid, right? Okay, so that works. What else could we do? Let's see. This one's like 6, 8, what? 16, 8, 6, 7 or something. Okay, and then that should have a 1 in it. Okay, it should not have a 2 in it. Okay, yeah, that's the problem. How could it have a 1 and a 2? Oh, it does. Okay. It should not have a 3 though. Okay, that is the problem. So we divide by 3 once. So let's see, 16, 8, 6, 7 over 3. Oh, greater than or equal to 3. Oops. Okay, that is the problem. Okay, so that should be fine. So only if it's not in the grid, it could add to it again. I don't get it. What's the problem here? Oh, not 3. Okay, that would be pow. Oh my god, bruh. Pow 3 comma that. Okay, that makes a lot more sense. Let's go, let us go. We got all the things that we could possibly make. So 0, 0, that makes sense. 1, 0. Okay, let's go. So now we just need to check if any of these guys are winning, and we are good. So we'll just make a check winning function, and we should be done. Bool, check winning. Int grid. And how do we do this quickly? There's no way to do it quickly. I'll just write it up. It's like, you guys know the idea. You just like, you just bash it. But let us first make a get element. Int grid. Int, and basically to divide by like the power, right? So you just do grid over equals pow 3 comma int, and then you just return grid mod 3. So I'll just write it. You guys don't have to wait for me. I'll speed this part up. Okay, nice. I think we finally got a working checking thing. Look how beautiful this is. Holy moly, bro. What the heck? Okay, let us try it. 13? Why 13? Holy moly. No. That's not right. Okay, let's see. What are we printing out even? Cout. I want that. Okay. And where did we get a 7? Cout. Huh? Okay. I don't know why there's multiple things, but let's try it. Oh, I see. Okay. So which ones are winning? Let us print out the boards. Display, grid, and then, or no, I, and then cout endo. 1, 1, 2, that's winning, that is winning. Is that even possible though? Okay, that is possible. Winning. Oh, how is this possible? 2, 0, what? Gboards I. How did it even get a M over there? What? Let us see. once you win. Okay. So if new board is winning, then we don't. Okay, so if not V boards. Okay, if it's not winning, then we push it. If not, check winning, new board, then we push it. Okay. Because once you start winning, then you don't want to actually do anything. Okay. Ah, let's go. Let us go. I think we have it working. Okay, let us see. Let's get rid of all the display grids. Let us download it, and we should be good. Okay, moment of truth. Come on, let's go. Hey, let's go. Very nice, very good stuff. Okay, let us move on to problem number 2. Do you know your ABCs? Very nice. Okay. So, Farmer John's cows have been holding a daily online gathering on Moose, very nice, a video meeting platform for fun. They have invented a simple number game to play to keep themselves entertained. Okay. Elsie has 3 positive integers ABC. These integers are supposed to be secret, so she will not directly reveal them to her sister Bessie. Okay. Instead, she tells them some 4 to 7 integers and claims each one is one of these, and she may be lying. Oh, what? Oh, okay. Some may not contribute to a valid triple ABC. So, we basically had to figure out how many possible triples there are. Very nice, and we have 100 things. Okay. So, I mean, I did the bronze version of this problem, I think. I forgot I did the bronze question or something, but I've seen something similar. But basically, the main, idea is that A is less than B is less than C, right? Which means that A plus B is greater than both A and B is also less than A plus B plus C, right? Actually, we know specifically what order it is. In fact, we know that A B. Well, okay, so we know A plus A is less than B is less than A plus B. We don't know whether C or A plus B is bigger, so these might be the same. Then we know that's less than A plus C. We know that that's less than A plus or B plus C. And we know that this is all less than A plus B plus C. So basically the only 2 possibilities is these 2 are flipped, right? Either the first 2, they might give us 4, so they might give us the last 4, they might give us any 4, so that's kind of tricky. But if you're given all 7, you know that these 3 are either A, B, and A plus B, or A, B, and C. So, essentially, so I guess we could even assign these 4 to anywhere over here, because that would be 7 choose 4, and then just solve the equations, right? You basically say let's see, let's try it out. So essentially you could assign the 4, 5, 7, 8, you could assign it 4, 5, 7, 8, you could assign it 4, 5, 7, 8, you could try all the possibilities, but you have 3 unknowns and you have 4 equations, right? So you're guaranteed to be able to solve it. So all we got to do is figure out a way to get A, B, and C, and then we are good. Because once we get A, B, and C, we could generate the rest, and then once we generate the rest, we could just check whether it's consistent with the given thing. Okay, so let us think how to do this efficiently. So I don't want to write a equation solver because that is kind of time consuming. But there should be a way to write it so that we um we don't have to do any special casing. Because I think a lot of people in the actual competition they were like, okay, let's just go through every single possible case of how we could assign them and then do special casing for that. But that is a waste of time. Let us think smart. Okay, so let us think. There are 4 non-single ones, right? So in worst case, we're not given any single ones, right? In which case, we could basically add the 3. Oh, I see. Oh, huh. I guess we had to subtract it from here. Well, okay, so you could basically represent the assigning is you can have a 3-digit binary number, right? So essentially, A, B, and C contribute to, correspond to 1, 1 0 and 1 0 0, right? Because or the 0 0 1 0 1 0, right? Then you could say that let's make it nice and easy to understand. So A is 1 0 0, B is 0 1 0, and C is 0 0 1. Or sorry, 0 0 1, yeah. So essentially you could assign each of the 4, 5, 7, and 8 one of these binary numbers, and then that corresponds to one of these, right? And then how do we solve it given some random binary numbers? Okay, a nice thing that you might notice is that you at least have to have one of you can't have all 3 of the same number of things, right? You could either have um 1 and 3 of the 2s, or you could have um one one of the or 3 of the 2s and 1 of the 3s, but you can't have only 2s or only 1s or only 3s, right? So you're guaranteed to either have a 3 or a 1, but no. Well, yeah, you're okay. Let's see. So one way you could do it is you could just bash it out and try all subtract them randomly and then just see which ones you get, but that is kind of yucky. Oh wait, there might be multiple possibilities is what it's saying. Okay, I see. Well, yeah, it for sure could have multiple possibilities, but for each assignment there's only maximum 1, so we just have to check if that one assignment works. And if we do it for 4, then we just apply the 4 to like any of the other ones and then just like list out all of them. So we only had to get it working for 4 and then we are good. We could like, I don't know, we could assign this one. Well, okay, so assigning it's easy, but how do we actually solve it fast? Well, yeah, we could just try all pairs and just subtract them and see what happens, right? Because there's not that many pairs, we could just go through all of them. Okay, so essentially what we're going to do is we're going to like assign them to these binary integers. Then once we assign them to integers, then we could literally just like, we could just go through all pairs, subtract them from each other, and then eventually we'll end up with ABC, right? And once we get ABC, then we should be in good shape. Okay. Let us just code it up. I think it'll be easier to understand once we get into the epicness. Let us do it. C++, and what are we calling it? We're calling it dictionary ABCs. Let's call it ABCs, because I'm lazy to type out very long names, okay? So we got our using namespace, int t, comma n, and then we'll just do cin t for int I equals 0, I less than t I plus plus, cin n. Then we basically have, we had to read in our array, so we could basically take a vector int nums, and we could do for int j equals 0, j less than n, nums dot pushback, or well, we could probably c in something, int x, c in x, nums dot pushback x. Okay, so now what we gotta do is we gotta actually like assign each of these numbers to a binary number, right? So essentially the way we're gonna do that is, how are we gonna do that? So we could basically return a vector of assignments, right? Yeah, let's do that. Vector int. Well, I mean, there's a bunch of different assignments that might work. So we'll basically just go through assignments. Void generate, and then this is gonna generate assignments. And it'll just go based on nums, right? So vector int assignments. Okay. So first step, we resize assignments to the same as n, right? And then we want to assign all of n to something, right? So resize n, or nums.size. And the idea is we could basically, or like we could assign it, we have to do it in increasing order, right? Because obviously the smaller things in nums will like be lower things, like in A, B, C, whatever, right? Actually, that's not necessarily true, but let's see. Well, okay, so we will do like our options, right? We have a couple options. We could do int options 2, 8, and our options are 1, 2, 4, 3, 5, 6, 7. Or you could do the other way around, right? You could do 1, 2, 3, 4, 5, 6, 7. Okay. So essentially, we'll give like we had to keep track of our biggest, right? Int biggest and our int k, right? Where we are now. Okay, we should probably do this here, and we'll do assignments.clear over here. So we'll basically start our k from like 0, right? And we'll build it up. So if our biggest is like, I don't know, 0 over here, right? Then what can we do? Or we could just say if k is equal to assignments.length, then we're done. Then we just have to check whether the thing is right, and we'll check that later. Otherwise, we want to else then we want to just like for int I is equal to biggest plus 1, I less than 7, I plus plus, and we'll just say assignments k is equal to I, and then we'll recurse generate k plus 1 biggest, or now it's I. Okay. So eventually assignments is going to be something cool here, and then we'll actually have like our actual binary number, so bnums, and we will say bnums should also be resized here, bnums.resize nums.size, and we'll just say for int I in assignments. Actually, we don't need to, I guess we should do indexes, int I equals 0, I less than assignments.size, or we should just do less than k, I plus plus, bnums I is equal to options 0, comma I, or 0, comma assignments I. Okay, and then we want to check. Okay, so this should go after. Alright, seems legit. And we also want to do the other option for it being option 1. Okay. So now we assign binary numbers to all of them, right? So now we want to actually check the bnums. So we'll do void check, and once we check and it's good, then we want to add it to like a set of triplets. So we'll do set of, I don't know, pair int, or pair int, and PII, okay. And that's basically a triplet, okay. So we'll go over here, we'll basically go through bnums, right? Probably bnums up here too. Not that it really matters, but might as well. And the way we're going to check it is we're just going to like do all the subtractions necessary and find our first few numbers, right? So essentially, we'll say int r7, which are our numbers, or no, 8 we'll say, those are the numbers we have. And we'll basically go through it, right? So for int I equals 0, I is less than bnums.size, I plus plus, r bnums I is equal to nums I, okay. And then at the very end, we basically want to do for int I equals 0. Well, I'll just copy this basically. And if any of the r's are no longer equal after we like do our subtractions, then we got a problem. So if r bnums I is not equal to nums I, then we want to return. Otherwise, we want to add it. If it manages to get past all that, then we just do triplets dot insert, and then we add in our r1, which is a, r2, which is b, and rc, which is 4. Okay. Okay. So let us just stop that. Why is it trolling me? Okay, seems fine. So now we just need to do the subtracting part. And we should probably set it all to -1 originally. So now we're just gonna go through all pairs of the array, and if they could be subtracted from each other, we will subtract them from each other. And we want to keep doing that until what? We just want to do that until we get to our A, B, and C. Okay. For int I is equal, oh, okay, so while r1 is equal to -1, or r2 is equal to -1, or r4 is equal to -1, then we keep doing the pair thing. So for int I equals 0, I is 1, or I equals 0, I less than 8, I plus plus, and then for int j equals 0, j is less than 8, j plus plus, probably should be I plus 1 over here. And essentially we want neither of them to be -1, right? So if I, or like ri equal -1, or rj is equal to -1, then we have to continue. Otherwise, we got to check whether one is completely enclosed by the other, right? So if b, or if, so j is for sure greater than I, so that means that j for sure has to enclose I, right? Right? Or, yeah, so if something encloses something, it's for sure bigger than it. So if j mod I is equal to I, that means it's fully enclosed, in which case we could say rj minus I is equal to rj minus ri. Okay. And also, we should probably sort this first. Nums dot sort. This should be outside. Okay. Nums dot sort, or sort num dot begin. And we gotta include algorithm. Okay, and once we do this, this should be fine. This should work. Okay, let's try it. Seems risky though. Okay, so then we do generate 0, comma -1. Yeah, -1. Okay. Okay, let us try it. Okay, we gotta do our parentheses. Okay, so it doesn't error. That's good. Okay, so over here we want to do cout triplets dot size. Okay, so it's all 0. That is not ideal, but let us see. Oh, so over here we gotta set it all. So r3 is equal to r1 plus r2, and then r4 is equal to well, we already got that. So r5 is that plus that. R6 is 2 plus 4, and then this r7 is just 6 plus 1. Okay. Okay, so that's still not working. Hold up. Oh, I never even call it. Okay, check. And then check. That would make sense. 7, 1, 2, 3, 4, 5, 6, 7. Okay, so I tested both of them and it said neither of them worked, which is unfortunate. So, what was it getting for cout a r1, r2, and r4? 1, 2, 3, 1, 2, 4. 1, 2, 4 is what they got, so why wouldn't that work? So, r bnums I is not equal to nums I. Cout high. Okay, so it doesn't get past this. So r bnums, what? Okay, so 8 and 70? What, 70? How did num's I become 70? What? Bruh. Oh, 8 and 7. How did you get 8? Oh, okay, I don't know how that happened. Alright. Bruh. Okay. That would make a lot more sense. Let's try the whole thing. 1, 7, 1, 2, 3, 4, 5, 6, 7. Okay, so that's working. Then what about this whole thing? Why did this whole thing not end? Okay, why don't we put C out to the beginning of all our functions just to see where it's getting stuck. Okay, it's not getting stuck here. What? What's going on? I don't know. It works for smaller things, but why are they not ending for some? While loop just doesn't finish for some cases, I guess. Oh, I guess you need more stuff necessarily. Okay, so maybe we had to do some pluses too. So essentially, if they are disjoint, which means that it is equal to 0, then we could do plus. We could add them together. Okay, let's try that. Okay, what? Like, this should for sure get everything, right? So you could get minus, you could get plus. What else could you do? Okay, let's just for it, I guess, for int k equals 0, k less than 3, k equals plus. And what is our array? Cout r, or for I, int I, an array. Cout I space end all. Or no. Cout end all. Okay, what? Now why is it not doing anything? Let us see. How to get negative ones everywhere, dude? What? And array j is greater than array I. I mean, it should be, right? Because nums is in that order. Okay, so at least now it is assigned everywhere, but I don't know why it's not actually going through anything. So it'll go here, it'll go through all the pairs. If they're both negative 1, then it won't do anything, that's right. If j XOR with I is equal to that. What? Why does it only have like 3 highs in between each one? That's so weird. Okay. Oh, that makes sense. So let's see. Cout ij. Wait, what? Why did it even go into the loop? I'm so confused. What? Oh, for things that don't work, it might be messed up. Okay, I see. Oh, okay. So I guess if we have this, then we could just say, so I guess we should just do this like for 3 times, and if it doesn't work, then it doesn't work. For int k equals 0, k less than 3, k plus plus. Okay. Is 8 right though? No. Okay, so we're counting a couple extras then, I suppose. What are the triplets even? Oh, what? How? Okay, so we also need to make sure that they're in order of increasing. Okay, so we gotta check if R1 is greater than R2, or R2 is greater than R3, or R1 is greater than R3. Okay. Or we don't need 2 of these. Then we want to return. Okay. Okay, let's test this guy out. 1, 2, 4, 1, 5, 3. Oh, what? Done this, get rid of that? 2, oh, greater than 4. Whoops. Okay, nice. I think it is working. Let us try it out. Holy, that was so cancer. Okay. Should be fine. Nope. What? Okay, undo that. Oh, bro, I didn't even clear the triplets. Oh my god, dude. Holy. Okay, there you go. Oh, okay, I think now it's working. There you go, bro. Why do I meant to make the stupidest mistakes? Okay. Okay, and then here we just cout triplets dot size. Okay. Hey, okay, I think it's working. Let us try it out. Okay, plus work. Can we get a first try out of the question? Oh. Epic. Let's go. Alright, nice. And now finally for the last question, let's do it. Academia. Okay, so so this is another PhD program one, nice, driven by her love for computer science and also the lure of one day becoming Dr. Bessie. Having worked for some time on her academic research, she has now published N papers, and her paper has CI citations. Okay. So she's is measured by H-index. Okay, this is the same as the bronze version, okay. So she's planning to write up to K survey articles, each citing many of her past papers. However, she can only cite as many as L papers in each survey, okay? So before we were able to only add one at a time, but now we can add K at a time, basically. And we basically want to find, okay. So you can basically write K of those add ones to all of them. Okay, so the idea is now that we have another like factor to consider, right? So essentially, last time what we did is we basically binary searched, right? We would basically say, we could binary search on H. If we have H, how do we figure out how many we could get, right? So we sorted it 1, 1, 1, 100. And now we basically try like H is 2, which means that your top H guys have to be at least, your top 3 guys have to be at least 3. In which case both of these guys need to increase by 2, right? So before that was pretty easy, right? You just like say, okay, you just check if there's only well, actually it's impossible to get these to 3, which is why that wouldn't work in the previous one. But what could we do? Well, basically what we could do, let's think. So binary searching is for sure the right way to do it, but how do we how do we figure out whether these guys could actually get to the thing we want? So we only care about the things less than 3, right? So the things that are less than 3 are these guys, and how do we know if they could all get to so we know that they have to be at least within K of 3, right? So these guys are fine if K is equal to 2. This is 414, what is it? NKL. So in this case, she could do 4. She could increase all of them by 4. Or no, she writes 4, but each one only cites 1. Yeah, so that's why you could increase both of these by 2, like cite each one twice in 2 papers, and then you get to 3 for both of them. But then for this one, you can only get 2 because this doesn't work anymore. Okay, so let's think about it this way, right? So as long as they're within K, then essentially you just need to have Okay, let's think about it greedily, right? So essentially you want to like first increase the biggest guys. So okay, so I guess like in your first paper, you basically try lifting up all the bottommost guys, right? And then you do like the L bottommost guy. Okay. Then in the next paper, you would do the L bottommost guys, and so on and so forth until like all of them become like up to 3. So, so essentially you have like you had to like hit like X many things in each column, right? And then you had to hit like some amount. So like the maximum number of papers you could cite is KL, right? Like that's the maximum number you could cite. But if you have less than KL, are you guaranteed to be able to do it? Okay, let's just say each survey is like a binary number, right? So essentially each binary number could have like L1s, right? And there's K of these binary numbers, right? And essentially you want these binary numbers to equal however much each one needs to get to the top, okay? This is kind of hard. Let's see. If you add like, can we just do it greedily, right? Like, so the L smallest guys at any point will get a plus. Well, okay, if there's 2 equal guys, right? Like, it doesn't matter which one you take, right? And it always makes sense to put the smaller guys in first, right? Okay, so yeah, we just had to check if the first guy is within K of what we wanted to be, right? And then we had to check that the number of guys or like number of citations we need to do is less than KL, and we should be good. So let us code it up. Okay, academia it is. Using namespace int n, k, and l. And then the actual citation, so int c. Alright, read it in. And basically the way we're going to find if the sum is less than KL is we're just going to like, what are we going to do? We are just going to use prefix sums, right? We could basically find the sum of any like range of numbers. So, actually, I guess we had to be a little bit careful. So log n times n. Okay. So for a given h, it's pretty easy to do prefix sums on it, so should be fine. Then we do c for int I equals 0, I less than n, I plus plus, c in ci, and we'll just do sort c comma c plus n. Then we will do binary search on h, so we'll do int low is equal to 0, int high is equal to 1 or like 200,000. We could just put that, doesn't really matter. And then for int I equals 0, well, we probably do 100,000 just so we don't out of bound ourselves. And then while low is less, or low plus 1 is less than high, then we gotta do if check or mid, we'll say int mid equals low plus high over 2. if check mid, then we set low is equal to mid, otherwise we check, or otherwise we set high is equal to mid, and then at the very end we just see out mid, okay, or we see out low, yeah, low, okay. So now we just gotta code up our check function, so bool check int h. So basically we gotta make our prefix sum, so we'll do int psum 200,000, and we go from the back, right? So essentially what we'll do is we'll go for int I is equal to n minus 1, I is greater than or equal to h, right? So if you have 3, you do 4 minus 1 is greater than, okay, so it's, okay, yeah, it is n minus h, holy, this is complicated, okay, it should be n minus h, yeah, n minus h, and I minus minus, okay, so if the num, if the I is less than h, then we basically, we should keep track of where the first one is, or, yeah, we should keep track of where the first one less than the number is, so, oh, okay, yeah, I guess it doesn't work, so let's think, basically the problem is, like, let's just say that there are a bunch of guys, like, there's, L minus 1 guys who are, like, K, that need K more, right? Then let us say, that means that, like, L minus, or sorry, there are K minus 1 guys who need L, right? That means that, like, K minus 1 of the papers need to have, like, all L of these guys, right? But then there's one more paper that needs, like, I don't know, I think it should work, right? Oh, yeah. If there's another paper that needs, like, K minus 1 things, right? Yeah, so the last guy is just K minus 1. Okay, so, I mean, I'm kind of thinking of it like a block kind of game, right? You have, like, these stairs, right? And essentially what you do is you just layer on these guys, right? And then you layer on here. And then eventually these guys will be big enough, and then you rotate it, and now, like, these guys are, like, this kind of, right? And then you keep layering it on. Wait, so none of them actually get wasted, right? Like, none of these KL papers actually get wasted. So the only problem is if you actually had to go bigger than K. Or, like, wider than L, right? Or no, okay, so yeah, the area, like, all of the area is going to be used. Yeah, okay, so it should just be that. It should be fine, okay. So if, we'll do, we don't really care where this one goes. We just care about the prefix sum. Oh, do we even need prefix sum? We just need the the sum, right? Yeah, so we just sum it. Okay. So int tot equals 0. Then we just do tot plus equals h minus ci. Okay, well, first step we had to check if ci or cn minus h is less than h minus k. Okay. If it is less than that, then we're screwed anyway, so we just return false. Okay. Otherwise, no matter what, it should be fine. So we just find the sum. If the sum is less than, if return tot is less than k times L. Okay. And let's test it out. Okay. If it's less than n minus 1, okay. Okay, so if h is equal to 0, well, we know h0 always works. Does h1 always work? 1 is greater than 1. At least 1. So all of them are, all the CI are, oh, some of them might be 0. Okay, so I guess if h equals 0, return true. I mean, that shouldn't really matter. It's not going to check h. It already knows that h works. Where's the segmentation error coming from? Let's see. Okay, so, what? Okay, we'll just do n plus 1. Why not? Okay. 3. Okay, that's good. 2. That's nice. Okay, so if it works the first time, I'm going to be so happy. Holy moly. Let's try it. Hey, let's go. Easy. Very nice. No, what? Bruh. What? What did I do wrong there? Hello. I'm very confused. What? Wait, what? How big could the citations be? Oh, so you could have like 10 to the 10. Should I just... Oh, maybe... Okay, let's just try. Long. Why not? Let's just make sure that we're not trolling. Okay. Please be the problem, my guy. I beg. Please. Just do it. Just be the problem. I beg. Come on. Let's go. No, what? What? That made something else fail? Okay. I don't know how that works, but... What? How did another thing start failing? when I made this a long. Okay, that's kind of sketchy. Oh, maybe it okay, let's see. Yeah, that might be kind of sus. Okay, let's try that. So clearly something is changing when we do long, so there must be something wrong there. And the only thing that could possibly be a long problem is that I'll just make everything long if necessary. Oh, damn, it was a long problem. Let's go. Huh, thank God. Okay, we don't have to debug more. Alright, that is a wrap. We finally made it through all the silver problems of the 2021 US Open Silver Contest. Hope it was helpful. That took me so long, okay? I honestly spent so much time on this video, I don't even know. I don't know why. I was just making so many stupid mistakes, but it's okay, we made it through. Alright, well, thank you guys so much for watching. As always, if you enjoyed the video, leave a like and subscribe for more. Thank you guys so much for watching again, and see you guys next time.